Welcome to this Forge College Explainer. Today, we're diving into events and errors. We are going to be drafting the ultimate inventor's blueprint for translating EVM errors over to the SVM. Now, for some quick context, this explainer is part of our lesson on mapping Solidity events and error handling to Rust and Anchor, and that sits inside the broader From Solidity to Rust and Anchor module, which is a key piece of our entire From EVM to SVM transitioning from Ethereum to Solana track. So if you've been following along, you know that translating code is really only half the battle. We have to translate the intent, and a massive chunk of that intent lives in how your program basically screams when something goes wrong.
Here's our engineering schematic for today. We'll hit 6 main sections. First, the translation blueprint. Second, anatomy of a pattern. Third, Solidity to Anchor translation. Fourth, testing and diagnostics. Fifth, the quality checkpoint. And finally, number 6, finalizing the catalog. Let's just jump right in.
Section 1. The translation blueprint, from code to catalog.
Okay, so in our previous lesson, error handling patterns, Solidity to Anchor, we conquered the actual mechanics of mapping those patterns. But here is the hard truth, guys. Without standardized documentation, your brilliant translation is basically just trust me bro code. And spoiler alert, trust me bro definitely does not scale in a professional Web3 engineering environment. That is exactly why we need what we call a pattern entry. Think of this as the Rosetta Stone for your engineering team. It's a meticulously formatted draft that documents an event or error translation. It verifies that the semantics actually survive the jump between chains, and it empowers your whole team to scale their Solana translation seamlessly without constantly reinventing the wheel.
Section 2. Anatomy of a pattern, the 5 minimum elements.
Because a proper blueprint needs specific, standardized components to actually be usable by anyone else on your team, right? You can't just hand over a scrap of digital paper with some Rust code scribbled on it. There are 5 absolute minimum elements your pattern entry must contain. 1. Side-by-side code examples. 2. A diagnostics section. 3. Completely clear reproduction steps. 4. Pitfalls and translation notes. And 5. Suggested tests. Honestly, if you hand over a code snippet to a reviewer without these 5 elements, you can absolutely expect it to be sent right back to the drawing board.
Out of all of those, the absolute most crucial piece of the puzzle is the diagnostics mapping. This explicitly links the original observable signals from Solidity, like a text string revert or maybe a specific log topic, directly to an anchor observable signal, like an emitted program log or a custom numeric error code. This mapping is exactly how a developer who's debugging a Solana transaction knows they're staring at the exact equivalent of an Ethereum revert. It's the aha moment for debugging.
Section 3. Solidity to Anchor translation, side by side.
Let's roll out the patent paper and actually ink out how these two ecosystems compare directly, side by side. Notice how Solidity relies heavily on explicit required checks that revert the entire transaction with a hard-coded string message. It works, sure, but it's a bit like slamming a heavy, gas-guzzling vault door. Over in the Anchor ecosystem, things are much more elegant. Anchor utilizes program-level result returns and defines custom errors using an error code in a macro. So instead of just shouting a raw text string into the void, you're passing back a highly structured error variant.
And we see the exact same philosophy with events. In Solidity, you might just hastily write emit value set and toss in msg.sender and a value. But in Anchor, we use the emit macro, and we pass in a struct that's been specifically decorated with the event macro. The Anchor runtime takes that, formats the program log beautifully, and prepares it for off-chain clients to decode. That is how you achieve true event parity between the networks.
Now at this point, you might be thinking, hey, why don't we just copy the exact Solidity revert strings over to Anchor? Wouldn't that keep our lives simple? Well, no. Anchor doesn't really work that way. To save precious space and compute at runtime, Anchor uses numeric error codes on-chain. Those rich, human-readable strings, they are only mapped back to the numbers inside developer tools and client SDKs. Direct string replacement simply isn't how the SVM operates, so we have to adapt our mental model.
Section 4. Testing and diagnostics. Proving it works.
Because, look, a brilliant blueprint is completely useless if the machine fails the test run on the factory floor, right? We need rock-solid, incredibly clear reproduction steps to prove the translation actually holds up. In your pattern entry, you must outline explicit steps for both environments. On the Solidity side, you tell the reviewer to run npx hardhat test to ensure the original code reverts or emits exactly as expected. Then you have them run anchor build and anchor test. And in that anchor test, they shouldn't be looking for a string. They should be asserting the return of the specific numeric code, like a ProgramError.custom variant.
To build a truly airtight case here, you actually have to include at least 2 distinct verification checks in your pattern. One check has to confirm the behavioral state, as in, did the transaction actually halt when the value was too high? The second check must confirm the observational outcome, meaning you need to assert the exact emitted log substring or the exact integer of the error code. You need both to prove it works.
Section 5. The quality checkpoint, the QA phase.
Before this blueprint goes off to the final capstone review, it must pass our rigorous quality assurance checkpoint. Think of this as the final, unforgiving inspection on the assembly line. And the magic number here? 20. 20 minutes. That is the strict maximum time box any reviewer should need to clone your repository, compile both the Solidity and Anchor code, and reproduce your results locally. If it takes 21 minutes because your setup instructions were messy or you forgot to list a dependency, immediate fail. Right back to the drawing board.
Reviewers are going to be walking through your work with an unforgiving acceptance checklist. They'll scrutinize your Solidity snippet, your Anchor snippet, your diagnostics, and your repro steps. For every single item, they need expected evidence. It needs to compile, it needs to run via Anchor test, and it needs to generate sample logs using local commands. If even one element is missing or vague, your pattern is marked for revision. It's tough love, but it's necessary.
Section 6. Finalizing the catalog, wrapping the artifact.
But hey, once your draft flawlessly passes those checks, congratulations! You've successfully created a robust, finalized artifact that is ready to be added to the official pattern catalog. Completing these 5 sanity checks, the compile check, the behavioral test, the diagnostic match, the 20-minute time box, and the reviewer clarity check, guarantees that your translation is bulletproof. Meeting these pass criteria means your entry preserves the exact behavior of the EVM contract without any SVM ambiguity whatsoever.
And I want to pause here, because this is a really important lesson to internalize. Documenting translation-specific pitfalls in your pattern entry isn't just about covering your tracks. It is the pedagogy. It is where the real teaching happens. When you explain why an error enum is better than a revert string, you are educating whoever eventually inherits your codebase. You're taking a simple code swap and turning it into an architectural masterclass.
So, I highly recommend you keep this core philosophy plastered on your virtual wall as you work. Preserve observable signals, make reproduction trivial, and document translation-specific pitfalls. If you do these 3 things, you transform isolated ad hoc code conversions into highly reusable, scalable patterns that are going to save your team literally thousands of hours. So, what's next for us? In our upcoming lesson, we're going to take a step back and look at the macro view. We'll assemble multiple draft entries, just like the one we designed today, and we'll categorize the overall catalog ordering based on review time and translation difficulty. Basically, we are moving from drafting a single entry to curating the entire library.
I want to leave you with this provocative thought. If a brand new developer inherits your translation tomorrow, will they instantly understand the why behind it, or will they just be staring at a pile of "trust me bro" code? Are your blueprints truly robust enough for the real world? Thank you so much for joining this Forge College Explainer. To master the transition from EVM to SVM and dive much deeper into this topic, please visit forge.college. Until next time, happy coding.